The first thing we want to notice is that this motion graph has 4 different parts to it. Alrighty, let's get started with these graph translation notes. So when we say graph translation notes, what we're really talking about here is looking at a motion graph and using the information in that graph to make another graph. Specifically, the graph that we're going to construct here is a velocity versus time graph. So we're going to take a displacement versus time graph, use the information there, make a velocity versus time graph, and then do the same thing with the information in the velocity versus time graph and build an acceleration versus time graph. We'll show exactly what key pieces of information we need in order to do that in just a sec. I recommend when you see these types of problems to break it down into steps. The first step I think that we should all do is divide the graph into parts that have equal motion. Alright, so just like I mentioned before, this graph has 4 different parts to it. I've already gone ahead and broken it up. Just a reminder, the way that we know that there's different parts of motion is by looking at the shape of those lines. So we can tell an object's motion based off of the slope of its displacement time graph. So anytime we notice a change in slope, that's telling us that there's a change in motion. Now that we've identified the 4 different parts to this graph, we need to calculate the slope of each of these parts. Remember, the slope of this graph is going to tell us how fast the object's moving, in other words, the velocity. Some of you may notice that there are certain parts of this displacement versus time graph that we aren't going to be able to calculate the slope of. So let's get started with calculating these slopes. Let's start with line number 1 here. So for line number 1, we're just going to do rise over run, right? That's how we get slope. So we're going to count up and we see that we start at 2, we're ending at 6, so that's 4. And then we're also starting at 0 seconds and ending at 4 seconds, which is also 4. So the slope of line 1 would be 4 over 4, in this case 1. The units, meters over seconds, because our y-axis is displacement, which is measured in meters, and our x-axis is time, which is measured in seconds. Now let's look at the second line here. Well, we can see it's a horizontal line, so we know that the slope of a horizontal line is just 0. We need to remember though, it's not just 0, it's 0 meters per second, because slope has units. Now it's time to tackle line number 3, but like we said before, we can't do that because we cannot calculate the slope of a curved line because it's always changing. Something though that we should notice about this curved line is how that slope's changing. So we can see that initially we're starting out with almost a horizontal line, and as the line continues it gets steeper and steeper and steeper. So if my motion on this line is starting off very slow, and we're saying at the end it's very steep, meaning that it's moving very fast, we can infer that we're speeding up along that curve. Now let's take a look at line number 4, and over here we're going to notice that it's pointing downward, so that's going to give us a negative slope, and again we'll just count rise over run, down 3 over 2, that's going to give us negative 3 over 2. And again, slope has units, so it's going to be meters per second. Now that we've calculated all of those slopes, or in other words, all of the velocities of those different parts of motion, we're going to take that information and plot it on our velocity versus time graph below by looking at the y-axis. Let's start with line number 1. We'll notice that line number 1 has a velocity of 1 meter per second, and that motion is present for 4 seconds. So we'll go down to our velocity versus time graph, find the velocity of 1 on the y-axis, and then just draw that velocity over for 4 seconds. The reason we have a horizontal line on our velocity versus time graph is because the motion that's taking place during that 0 to 4 second mark is a constant motion. We said a constant motion happens when we have a straight or sloped line. In this case, our displacement versus time graph has a sloped line. Now let's look at line number 2 and translate that motion over. Well, we said line number 2 had a slope of 0 and that was present from 4 to 7 seconds. So 4 to 7 seconds, we're going to find 0 on the velocity axis and we're going to draw another horizontal line. So we're going to skip over line number 3 at this point. We'll just put a question mark there because like we said, we don't know what the slope is of that line. So we can't draw it on our velocity versus time graph at the moment. So let's look at line number 4 real quick. And remember, line number 4 had a slope of negative 3 over 2 meters per second. So we're just going to do the same thing we did before. We're going to locate negative 3 over 2, or negative 1.5, on our velocity, and then we're just going to draw a horizontal line during that time interval, 9 to 11 seconds. Now that we know what the velocity is on the left and of the right of that question mark, all we're going to do is just connect the two lines. The reason we can do this is because we know the velocity that we were moving at before, and we know the velocity that we're ending at. So by us connecting those two lines, it's saying that we need to go from some beginning velocity all the way down to some ending velocity. Now, in order to get our acceleration versus time graph, we basically just need to repeat all the steps that we did with the displacement versus time graph, but this time looking at the velocity versus time graph. So the first step that we did, right, was breaking down these pieces of motion. I've already broken them down to you by drawing them in other colors. So now let's take a look at the first line, the blue one, and calculate the slope. Well, this one's a lot easier because we can just see that it's a horizontal line. So the slope of our blue line is 0 meters per second squared. We're going to do the same thing for our red and green line, also noting that there are horizontal lines, so they'll also have a slope of 0 meters per second squared. Now we're going to look at our light blue line and calculate that slope. We notice that this line is pointed downward, meaning it's going to be a negative slope. We take the rise over run, and we end up with negative 1.5 over 2, which is equivalent to negative 3 over 4 if we don't want to have a mixed fraction. And again, our units are meters per second squared. I'm just going to go back really quick and fix the other ones to the correct units. Some of you may be asking, but Mr. Weiss, how did you get those units? Well, I'm glad you asked. I'll show you really quick. We know that slope is the change in y over the change in x. Our y here is velocity, which is measured in meters per second, and our x is time measured in seconds. So the units would be meters per second over seconds. That's going to give us meters per second squared. We'll notice here that meters per second squared is actually the units of acceleration, and we can see that on our y-axis on our graph below. Now we're going to look at the slopes that we calculated from our velocity versus time graph and just bring them down below. The slope from 0 to 4 seconds is just 0 meters per second squared. So we're going to draw a horizontal line from 0 to 4 seconds. Then we're going to look at our next slope from 4 to 7 seconds, and we're going to notice that's also 0 meters per second squared, so we're going to draw another horizontal line. Lastly, we're going to look at our time from 9 to 11 seconds. Notice it is also 0 meters per second squared, so we'll draw another horizontal line. Now that we have drawn all the 0 acceleration points, we're going to look at the time from 7 to 9 seconds, and that slope, notice it's negative 3 over 4 meters per second squared, and we're again going to draw a horizontal line. All of the lines that we just drew were horizontal lines. The reason being that they all had constant slopes. So again, we're just graphing the slope, and since it's a constant value there, it's going to produce a horizontal line. Let's summarize everything that we've gone over in these notes. First, let's start with the slope of our displacement versus time graph. We said that the slope of our displacement versus time graph gave us the change in distance over the change in time. That's the velocity. We also know that because slope produces the units of meters per second, and those are the units of velocity. Next, let's talk about the slope of a velocity versus time graph. The slope of a velocity versus time graph is the change in velocity over the change in time. This gives us acceleration. In other words, we're saying how quickly can we change our speed. Another reason why we know that the slope of a velocity versus time graph gives us acceleration is because the units of the slope are meters per second squared, and those are the units of acceleration. Now that we've discussed slopes, let's talk about the curves of those lines and what that means on those graphs. If our displacement versus time graph has a curved line, that means that we're experiencing some sort of acceleration. When we say acceleration, we mean that we're either speeding up or slowing down. Let's just quickly review which type of line produces a speeding up and which type of line produces slowing down. So like we said before, the slope of our displacement versus time graph is going to tell us the velocity. So if our slope is getting steeper and steeper, that's going to mean that we're speeding up. The two curved lines that will produce that is a curved line that ends pointing upward or a curved line that ends pointing downward. The reason being, if we were to take that curved line and break it up and find out the slope at each of those individual points, we would see that initially we're starting off with a horizontal line, meaning that we aren't even moving, we have 0 velocity. And at the end, our slope is getting steeper and steeper and steeper, meaning that we're moving faster and faster and faster. Since those two different types of motion are happening in one time interval, we can classify that as acceleration. On the flip side of speeding up, we also have slowing down, and that's just going to be the complete opposite, right? We're going to start with a slope that is very steep, almost a vertical line, and then we're going to end with a slope that is more of a horizontal line. When in doubt, just find the slope of the line at the beginning and the slope of the line at the end. If those two slopes match, then we know that it's experiencing constant acceleration. If those two slopes are different, meaning that we are getting bigger as that line progresses, then we're speeding up. If we're getting smaller as that line progresses, then we're slowing down.